In this lesson, we're going to look at some ideas of what we call relations and functions and how they relate. So we first of all need to look at some definitions. And we're going to look at the definition of a relation is a set of ordered pairs. So we can have look at relations in several different ways. We could talk about the set of ordered pair of and because it's a set, we have to put it in our set notation. They're ordered pairs, so we could have 2, 1. We could have the ordered pair 3, 5, 4, 1, 6, 8, 2, 5. And this would be a relation. It's a set of ordered pairs. There's not any particular number of sets that you have to have in your relation. It can be anything from 1 to infinite, but it's a set of ordered pairs. Now, the domain is the set of first coordinates. Many times we'll call those the x's. They're not always x's though. So the domain is the set of first coordinates. So in this relation that I just wrote, our domain would be 2, 3, 4, 6, and then a 2, and I don't have to write it again because I've already got it written. So that would be our domain. The range is the set of second coordinates. Many times that will be our y's, but not always. We can use other letters, so that would be 1, 5, 1, which I don't have to put down, 8, and 5. So this would be a relation. It's simply a set of ordered pairs. And you will need to be able to take a relation and give the domain and range. Now, we also have what we call functions. A function is a relation, so that means it's a set of ordered pairs. But it's a relation where each element of the domain is paired with exactly one element of the range. So if I went back to the relation that we looked at just a while ago, in this case, the element 2, which is a member of our domain, is also used twice. So in this case, we have one element of the domain is paired with 2 different elements of the range. So this relation would not be a function because every element of the domain is not paired with exactly one element of the range. We have the 2, 1, and we have the 2, 5. Let's look at another example. If we had the relation uh, 1, 2, 3, 4, 5, 6, okay, this would be an example of a relation, and this is also a function. This would be a function because each element of the domain, 1, 3, and 5, are paired with exactly one element of the range. So this would be an example of a function. If we look at the relation 1, 2, 3, 4, 5, 6, 5, 8. Okay, this is a relation. It's a set of ordered pairs. But again, we have 2 elements of the domain, or we have one element of the domain that's paired with 2 different elements of the range. So this one would not be a function. Now we need to be able to determine if something is a function even if it's not listed as a set of ordered pairs. So we want to look at functions that are given as equations. If we're dealing with functions as an equation, that's where you're talking about something like y equals 10 plus 3x or y equals x squared minus 2. So we're looking at functions as an equation. Now, when we do, the variable x is called the independent variable, and it would be our domain. The variables x give us our domain. So the domain is the set of independent variables. The variable y is called the dependent variable. So it's our dependent variable. And our dependent variable is also the range. So when we're talking about the range, we're talking about the set of second coordinates, which in an equation, that would be our y's, and we're talking about the dependent variables. You can see up here in this equation, y depends upon what x is. If x is 1, y will be 13. If x is 2, well, y will be 16. So we pick the x, and then the y depends upon what x we pick. Now, to be able to tell if an equation is a function, then you want to solve your equation for y. And if when it's solved for y, then more than one value of y can be obtained for a given x, then the equation does not define a y as a function of x. What you do is you find one value that would make an exception. So let's look at a couple of examples of some equations and decide if these equations are functions. If we took the equation x squared plus y equals 4. We want to solve this for y, so we're going to subtract x squared from both sides, so y will equal 4 minus x squared. Now what we want to do is think about our values for x here. If we plugged in a 1 for x, and we could just make a table. If we plug in a 1 for x, then we're going to have 4 minus 1 squared, which will be 3. Is there any other value for y that we could get when x is 1? Well, there's not. There's only one value. If we picked a 2, well, then we would have 4 minus 2 squared, which would be 4 minus 4, or 0. Well, again, there's no other value that we could get for y when x is 2. If we picked a negative 1, well, 4 minus, okay, negative 1 squared is 1, 4 minus 1 is 3. There's no other value for y that we can get when x is negative 1. So for every value of x, we're only going to get one y. So this would be a function. Okay, let's look at another one. Say that our equation is x squared plus y squared equals 4. Now the first thing we want to do is to solve it for y. So we'll subtract x squared. And we will then take the square root of both sides. And if you remember, when we take the square root of both sides, we always have to say plus or minus. So right here, let's pick a value for x. If we picked for x 1, well, 1 squared is 1, so 4 minus 1 is 3, but we're going to get plus or minus the square root of 3. So right here for this one value of x, we got two different y's. So this would not be a function. So this is not a function. If we looked at this one. So one thing that we're going to notice right here is that we can't have a y squared in our function. And it be a function. If we have a y squared, then it's not going to be a function, because when we solve for that, then we're always going to come up with two different x's. And in fact, we're not going to have y to an even power. If y is to an even power, then it's not going to be a function. Let's say we had xy plus 2y equals 1. Okay, we want to solve this for y. Well, to do that, we're going to have to factor out the y. So y times x is xy, y times 2 is 2y equals 1. Then we can divide both sides, and we get 1 over x plus 2. Well, again, if we start picking values for x, we're going to see that we're only going to get one value for y. If x is 1, then we're going to have 1 over 3. There's no other number we can get. If x is 2, we're going to have 1 over 4. And there's no other answer that we can get. Now we do know that in this one x cannot be negative 2, because then that would make that 0 as far as solving for y. But as far as substituting in a negative 2 up here for x, we would still get a value. So we changed our equation here. So it's not a case that we have to eliminate a variable. That was not our, we made an equivalent equation. And so as far as working with this, if just substituting in. But if you solve it for y, then we can't use our negative 2. So those are some of the things that you can do to look at an equation to decide if that equation is a function. Is to go through and solve it for y, and then see, and it's kind of a thinking through process of, is there any value for x that would give you more than one y? And the main time that that's going to happen is if you have a y squared. Okay, then we can look at what we call our function notation. And in our function notation, it's going to be written as f of x. And that's how you read this, is you will read this as f of x, and your value then is, this is not f times x, but it's read f of x, and that represents the value of the function at the number x. So we would have a function written, and we'll know that these are functions because they're written in this form. So f of x equals x squared plus 3x plus 5. Now what we want to do then is to evaluate this function at different values. So let's say we wanted to know what f of 2 is. Again, this is not f times 2. We're not going to be solving for f. This is a function. You can think of this letter out here as the name of the function, because we'll also talk about g of x and h of x, which means that they're different functions still in the variable x. So what we want to do here is we want to take the function named f, and wherever there's an x, we want to replace it with a 2. So we would have 2 squared plus 3 times 2 plus 5. And if we did that, we would have 4 plus 6 plus 5, which is 15. Now that's what our function is equal to when f is 2. We could also write that then as an ordered pair. The 2 is our domain or independent variable, and 15 is our range or our dependent variable. So this is our x value, and the 15 is the same as our y value. And there will be some things that we'll do later that even though it's written as f of x, we will change that f of x to a y when we're dealing with finding our inverse functions. We could also be asked to find f of x plus 3. What this means is to take the function f And wherever there's an x, we're going to plug in an x plus 3. So we would have x plus 3 squared plus 3 times x plus 3 plus 5. Evaluating this, we would square this, so we would multiply x plus 3 times x plus 3, and we'll get x squared plus 6x plus 9. We've done that quite a few times, so I'm not necessarily going to go through the whole multiplication. Some of you may know the pattern of the first term squared, twice the product, plus twice the product of the two terms, plus the last term squared. And if you do, that's fine, but you just go through and multiply it out. Then, using our distributive property, we're going to have 3x plus 9 plus 5. Combining our like terms, we get x squared plus 9x plus 18 and 5's 23. It doesn't matter what you substitute in. We could even go through and substitute in, say we want to find f of negative x. That means take our function, wherever there's an x, we're going to plug in a negative x. So we would have negative x squared plus 3 times negative x plus 5, or the opposite of x is another way of reading that. So that gives us x squared minus 3x plus 5. And again, this is a process we're going to do a good bit later on when we're dealing with our inverse functions. We could even ask to find something like f of a. That means we want to take our function named f, and wherever there's an x, we're going to substitute in an a. So we would have a squared plus 3 times a plus 5, which actually changes our variable. So this is what we mean by function notation. Now I mentioned that our functions can be labeled several different ways. We could have a function that is labeled or is named h of x. Wanting this. And for that then, say that that's defined to be x to the fourth plus x squared. Let's make that a minus x squared. Plus 1. And we could be asked to evaluate it at different values of x. So maybe we want to find h of 2. So we would substitute in for x. We would substitute in 2 and have 2 to the fourth minus 2 squared plus 1, which would give us 16 minus 4 plus 1, which would be 13. And you can write it in this way, that h of 2 equals 13. Again, don't try to solve that for h. That's not what this means. So, or you could write this as an ordered pair. When x is 2, then our y value, our dependent variable, is 13. We could be asked to find h of negative 1, which means wherever there's an x, we'll substitute in negative 1. Usually I try to substitute in parentheses, and that way I don't have to wonder, is that a negative, or is the negative before or outside? Because we've talked how, especially if you're using a calculator, it's going to matter whether that negative is inside the parentheses or outside the parentheses. And then plus 1. So we would have 4. Whenever you square a negative number, you get a positive. And where did I get a 4? That would be a 1. That's 1 squared. 1 to the fourth is 1. Then negative 1 squared is 1. Plus 1 would end up being 1. So we would have the ordered pair negative 1, 1. Let's look at one last one using this function. We want to find h of 3a. So we take our function, wherever there's an x, we substitute in 3a. We would have 3a to the fourth minus 2 minus 3a squared plus 1. Which would give us 81a to the fourth minus 9a squared plus 1. And so again, we have a different function there. Now, sometimes our functions can look a little bit intimidating, but it doesn't mean that they're difficult to do. So let's take a quotient. F of x equals 4x squared minus 1 divided by x squared. All we're doing is substituting in. If we want to know what f of 2 is, then wherever there's an x, we're going to substitute in a 2. Now, our order of operations says that we work the numerator, which we'll raise to powers first. So 2 squared is 4, times 4 is 16. We work the denominator, and then last of all, we're going to do our division. So we'll have 15 fourths. Now, we can't divide 15 fourths, so we will leave it as 15 fourths. Don't change this to a decimal. That's just a lot of extra work, and this gives us an exact answer. Or sometimes if you change it to a decimal, then it wouldn't be. Okay, let's say that we want to find f of negative 2. Then that simply means wherever there's an x, we'll substitute in negative 2. Be sure that the negative goes inside the parentheses. So when you square negative 2, you get positive 4 times 4 would be 16 minus 1. Negative 2 squared is 4, so we get 15 fourths. We got the same answer. Two different x values, but we got the same y value. And if we wanted to find f of negative x, simply means wherever there's an x, we're going to substitute in negative x. So negative x squared is x squared. So we end up with 4x squared minus 1 over x squared. We ended up with the same function that we started with when we put in negative x. And if you notice up here, what that meant was for f of 2, we got the same answer as f of negative 2. We'll also find f of 1 will be the same answer as f of negative 1. That when the sign changes, you're still going to get the same answer. Okay, what we want to look at next then is graphing our function. And we're going to graph our function simply by picking some points and going through those points and plotting them on our graph. We'll look at graphing functions a little differently in a different section. But let's say that we were given the function f of 2, f of x equaled 2x, and we want to graph this. Now, I'm going to give you then some specific points to do. We're going to just look at some specific ones as we go. And let's say that we're going to make a table. For our x's, we're going to go from negative 2 to positive 2. So we'll have negative 2, negative 1, 0, 1, and 2. Now what we're going to do with these is we're going to plug them into our function. And so we picked our x's, and we're going to find out then what our f of x is, which is going to be the same as our y. And so we're going to plug it into our function, which is 2x. So if we do this here, then we're going to have 2 times negative 2, which is negative 4. If we plug in a negative 1, we're going to have 2 times negative 1, which is negative 2. 2 times 0 is 0. 2 times 1 is 2. And 2 times 2 is 4. And then what we want to do is plot these points. So we're going to plot the point negative 2, negative 4. So we've got negative 2, negative 4. We're going to plot the point negative 1, negative 2. Plot the point 0, 0. Plot the point 1, 2. Plot the point 2, 4. Now, those 5 points aren't the only points that make up our function. There's a lot of others. So what we're going to do is we're going to take these points and we're going to then connect them with a line, and it doesn't have a beginning or an end, so we're going to deal with, it's going to be a line, but I'm going to just start it here. It's going to keep on going, and it goes forever in both directions. And I would really need a little arrow here on the other end to show that this goes in both directions. But that line represents all the points that makes this equation true. Now let's compare that then with another let's just change our function just a little bit and say f of x is equal to 2x minus 3. So again, we're going to pick those same 5 points. We're going to pick negative 2, negative 1, 0, 1, and 2. We're going to plug them in and find out then what our f of x is. So we'll plug in our x's, find our f of x. So it's 2x minus 3. So we would have 2 times negative 2 minus 3. Well, that's negative 4 minus 3 is negative 7. 2 times negative 1 minus 3 would be negative 2 minus 3, negative 5. 2 times 0 minus 3 would be negative 3. 2 times 1 minus 3 would be negative 1. And 2 times 2 minus 3 would be positive 1. Now if we graph these points, we've got negative 2, negative 7. We have negative 2, negative 5. 0, negative 3. 1, negative 1. And 2, 1. And again, if we connect these, we're going to have us a line. And one of the things that you might notice about those lines is that they are parallel. And every point here is exactly 3 units below every point up here. So it was the same function, but we dropped every point down 3 units. And in some of our future sessions, we're going to deal then with what we call transformations, where we can look at our equation and we can tell what's going to happen. But right now, all you're going to need to do is to be able to take your functions and graph them on the same coordinate plane. And if you don't have graph paper to do it, that's okay. You can draw your coordinate plane, but you're wanting to look to see then what happens and kind of start noticing, well, what happened to my graph and how did my equation differ? And that will lead us into some things that we're going to do later. But you'll just be given, we're going to do the points from -2 to +2, or it may be that you're given some specific points to make your graphing just a little bit easier. All right, there are times that once something is graphed, then we want to be able to tell if it's a function. And what we just graphed here, these are functions. For each x, there was only the possibility of having one y. This is what we would call a linear function. And when we graphed it, it turned out to be a line. But there's other graphs that we may have that we may want to know, well, are those functions? And to be able to tell, then what we do, or what we perform, is what we call our vertical line test. And all that we mean by a vertical line is if we drew a graph, let's say we have our coordinate plane and we draw that graph. If we go through and we draw a vertical line through any point on that graph, it only crosses that graph once. Now remember that if it's a line, that it goes on forever in both directions. So we may only show it as a segment here, but we're talking about forever. So this would be an example of a function. If we graphed a circle, well, that would not be a function, because if I draw a vertical line through this point, it's also going to go through this point. So for this x value, I have two different y values. So this one's not a function. This one would be a function, but this one would not be a function. And we'll have all different types of functions in our graphs, and we have to decide. But it's a very simple test that we can do, and we can know if something's a function. If we drew our vertical lines, this would be an example of a function. If we had as our graph something like this, that would not be a function, because when we draw our line, it's going to cross in more than one place. So you need to be able to look at a graph and then know if it's a function. You also need to be able to read from a graph some specific points. So let's take this graph that I've got drawn and look at it. And what we're going to do is we're going to find some specific points. So we want to find the point F1. And when we do, what that means is when x is 1, we want to know what our y value is. So we're going to go here to where x is 1. And we look at our y value for that, and we see that we're at 0. So our f of 1 value would be 0. Now if we go to f of 3, if you notice, when x is 3, our y value is 0 again. That's our value on our y-axis. So it's also equal to 0. If we go to f of -4, well, we have 1, 2, 3, 4. Here's -4, and we go up to our y value. Going to go up to our y value, and then we go over to our x-axis, and we see that that's 1, 2, 3, 4. That's +4. If we did f of 0, well, when x is 0, our y value is at 4. So it's just a matter of reading those values from the graph. And you need to be able then, given a graph, to evaluate some specific values. We also want to be able to find some things on our graph as we look at it from the domain and some intercepts and some different things. When we talk about finding the domain, what we're looking at is what x values are could we use with this graph. And so what we do is we look at our x-axis. And we look at how our graph relates to our x-axis. Which x's are we able to use? Well, you can see we're using all of these x's and coming up with values. And our arrows here mean that our graph keeps going out forever. And as it does, then we use all of our x values on the rest of the x-axis. So in this case, what we're using as our domain, what x's are available for us to use are all of them, all reals. And so the way that we write that down, if you remember, is we're going from negative infinity to positive infinity. Now for our range, we want to know, well, what does our x do on the y-axis, and how does it relate to it? What portions of the y-axis are being used? Well, you can see down here, this part of the y-axis, none of our graph covers it. What our y does, starting right here, and then it covers all of our points as we go up. That would be what our y-axis is. And so that is then our domain. Those are the y values that we're going to get when we use any real number. Remember, our y is the dependent. So our range, that starts at what, -4. It includes -4. And it goes to positive infinity. Now some things that we'll look for are intercepts. The x-intercept is where we cross the x-axis. Well, we cross the x-axis at 2 different points on this graph. And it may be that you never cross the x-axis. But where you cross it is called the x-intercept. So we could write those as the x-intercept equals, in this case, 1 to -3. And the x-intercept equals 1. Now we don't just put down x equals -3 and x equals -1. That is how we would write a vertical line. So we don't want to write it that way. We want to write it x-intercept, or we could write it as an ordered pair. We could write this as -3, 0, and this one as 1, 0. Those are your two choices. You don't have to write both of them, but that's how the choices of how you write something. Our y-intercept is where we cross the y-axis. Well, we cross it at one point here, so that would be y, the y-intercept, and that would be 1, 2, 3, -3. Or you could write it as an ordered pair of 0, -3. And then let's read some specific values. Let's find f of -2. So when x is -2, then our y value is down here. Now that's kind of hard to read because we didn't turn out on a specific point. So we're just going to have to estimate it. So when f is -2, it looks like that we're at about -1, -2, maybe about, well, let's just say -2.8. Or 2 4/5. You know, you can decide on that. At f is +2, well, our graph, it looks like it's going up. And again, if this line had continued, at +2, we might actually be at the point 3. And so we're going to be coming up with some specific points, but you just have to read those from the graph and figure out what they are based upon your reading it. And if it doesn't cross your grid marks at a specific point, then it may be a little hard to read and you'll just have to estimate it. Let's look at one more graph and figure up our domain. Now remember, our domain is our set of x values. So on this, if we were wanting to do that, then we're talking about where our graph is on the x-axis. Well, there's no graph out here because we had our circles at the end. That meant this graph stopped here. So our graph, our domain, starts here and it appears to end right here. Those are the values for our domain. So our domain then turns out to be uh, at negative, what is that, negative 6, and it doesn't include it. So we do the parenthesis, and then it stops at 0, and it does include 0. If we look at our range, well, again, that's our y value. We don't have any graph down here for these y values, but we do starting here and going up to there, and it stops because those didn't have arrows. If they had arrows, then we would keep going. And so the lowest value, you always start at the lowest, was negative 1, 2, 3. It included that point. The highest value is 1, 2, 3, 4, and it did not include that point. So that would be our range. Our x-intercept we cross at one place, which is negative 1, 2, 3, 4, negative 4. So you could write it x-intercept is negative 4, or as an ordered pair, negative 4, 0. Those are our two ways of writing it. The y-intercept we only cross at one place, and that's at negative 3. So our y-intercept is negative 3, or the point would be 0, 3. If we found some specific values, we want to find f of negative 5. So we have 1, 2, 3, 4, negative 5, 2 is about what that looks like. And again, your graphs are not exact, but negative 2. And then f of negative 2, we have 1, 2, and it looks like we have negative 2 there. This should have been a positive 2 over here. So f of negative 2 is negative 2. F of negative 5 was a positive 2, not a negative 2. Sorry about that. Positive 2. So you need to be able to know what a function is and be able to determine a function from ordered pairs, from an equation. You need to be able to graph some functions, find the domain and range. And then we will use all of this as we begin graphing our functions.